Math 287. I'm Joe Vasta, Cuesta College, and we are covering section 1.4. Separable differential equations, first order. First order is the highest derivative, which is the first derivative. Our first order differential equations in chapter 1 can be written as y prime equals a two-variable function. If you haven't had calculus 3, this right here is just an expression that has x's and y's in it. The differential equation is separable if you can write this expression on the right-hand side as a product with an expression with x's times an expression with y's. So here's some examples. Well, are these examples of separable differential equations? And the answer is we don't know. We have to see. Can we separate this by multiplication? The answer is no. This is not separable. Okay, so maybe we'll write that. And what about this one right here? This one we can separate with multiplication. There's g of x. There's h of y. So this one is yes. It is separable. Now this might be something you remembered doing in calculus 2. So it's probably exactly what you did in calculus 2, separable equations. Let's go ahead and solve some differential equations. Okay. So here's our example, y prime equals x. So this y prime is really dy over dx. Now on the right-hand side, it is separable. This is a function, we can call g of x this right here, and h of y is equal to 1. So we really don't have y's over there, it's separable. And if you have a separable differential equation, you can treat this derivative, dy dx, as a fraction. So when I do that, I'm going to multiply both sides of that equation by dx. When I do that, I end up getting dy equals x dx. So the next thing that I want to do is integrate both sides of that equation. The integral of dy, or 1 dy, is y plus a constant. We'll call that c1. And the integral of x happens to be x squared over 2 plus a constant, which we'll call c2. So y equals x squared over 2 plus c2 minus c1. Well, that c2 minus c1 is just another constant, which we'll just call c3. I'll just call it c. And there is the solution to this differential equation. So this differential equation, we're not solving for like numbers, x equals 7 or x equals 13. We're actually solving for functions that when you put into this differential equation, they'll give you x. So like if you take the derivative of this, you end up getting 2x over 2, so you end up getting x plus 0, which satisfies this differential equation. So this is a family of solutions, infinitely many solutions. This is called an explicit solution. An explicit solution means that it is solved for y. It is also, okay, so solved for y. It's also called a general solution because it contains constants. Or I'll just say it contains constant, which is right there. Okay, what I'm going to do now is I'm going to show you that we could have solved this differential equation directly. Now how does that work? Y prime equals x. So directly means I could have just taken the antiderivative on both sides. I'll go ahead and, next time we do this where we add a c on one side and add a c on the other side, we're always going to put the c's together. So when I solve a differential equation, I'll just go ahead and put the plus c on the right hand side. So if I take the antiderivative of y prime, I get y, and the antiderivative of x is x squared over 2, and then you have the plus c from both of the sides. And so, wow, why did we do it this way? Because this was a simple example and I wanted to illustrate the method of solving separable differential equations. Let's go ahead and look at problem number 2. Problem number 2 cannot be solved this direct method, and in fact it was the problem that we saw on the first sheet, the one that was separable. And so here it is. dy dx, or y prime, equals negative 6xy. This is separable. It separates. You can separate the x's and y's through multiplication. Here's our next problem. We'll get to it later. And so let's go ahead and multiply both sides by dx. Okay, the whole goal here is to get your x's on one side and your y's on the other. And I almost have it that way, except I have this y over here, so I'm going to divide both sides by y. dy over y equals negative 6x dx. Okay, now when I did that, and I divided by a y, now y cannot equal 0 as I continue. But let's look at this. If y equals 0, what does y prime equal? Y prime also equals 0. This right here is y prime. So you have 0 equals negative 6x times 0, 0 equals 0. Y equals 0 is a solution, a trivial solution. And sometimes when you solve differential equations and you divide by one of the values that would be a solution, sometimes you lose that solution. So at the very end of this problem, we should go back here and make sure that y equals 0 is contained in the general solution. Okay, let's continue. We will integrate both sides. The integral of 1 over y is ln absolute value y plus c, but we're going to put the c on the other side. I'm going to go ahead and switch back to black. This equals the integral of negative 6x, which is actually negative 3x squared plus, and I'm going to just put a c there. So this c represents the constant from this side and the constant from that side, and we put it over there. The next thing I'm going to do is I'm going to exponentiate both sides of the equation. I'm going to go, we have this equals that, so I'm going to say e to that ln absolute value y equals e to that junk over there. Now why did I do that? I did that because there's a property of logs that says if you have e raised to the log base e of something, you just end up getting that something. So what we have here is we have absolute value y equals e to the negative 3x squared plus c. That's all in the exponent. Okay, the next thing I'm going to do is I'm going to say that the absolute value of y equals e to the negative 3x squared times e to the c. Now this is the property of exponents, kind of like when you have like an x squared times x to the third, that gives you x to the fifth. You added those, so I mean, I'll show you that you have e to this times e to that, you add them. So I just kind of did this rule backwards. E to the c happens to be a constant. Now it's different than c, but what I'm going to do is I'm just going to write that as c, and I'll make the c in green. So that green c is different than that c up there, the black c. Now, lots of teachers would say you have to put a C1 here and a C2 here. We're going to skip that rigor and just assume that you know that e to the c is another constant c. Okay, so we have the absolute value of y equals constant times e raised to the negative 3x squared. We are almost done with this problem. What we have to do now is, if y is greater than 0, then y equals c e to the negative 3x squared. And if y is less than 0, y equals negative c e to the negative 3x squared. Now this assumes that c is positive, and if we have c as negative, we can go through some other cases. So I'm putting this in a cloud because in any case, and I didn't cover all the cases, but in all the cases, when you have absolute value y equals constant times some function, you're going to end up getting, whatever case you go down, a constant times that function. See, negative c is just a constant. So I'm going to go ahead and replace this with a purple c. And it could be the same c depending on what y is. E to the negative 3x squared. So I'm going to say in the future that the constant absorbs the absolute value. And so we have this right here. This is our explicit solution, because it's solved for y. It's also a general solution. There's a little sunlight right there. Because it has constants in it, but we can't box it yet because there's something we have to remember to do. We have to remember to check to see if it contains y equals 0. So is there a value of c, some real number c that you can put in there that will give you y equals 0? And it would be c equals 0. So this solution is contained in this family. Now sometimes you end up losing this guy. It's the equivalent of you have a big family and you leave one of your kids at the gas station when you're on a road trip. And it's rather embarrassing, but we should always check to make sure we have all of our kids. And so there's going to be a problem where we actually leave one of the kids at the gas station. There's the answer. Problem number 3. This IVP stands for initial value problem. Here's some initial values. And really what this means is you're going to go ahead and plug some values into your general solution to see which family member satisfies this. So let's go ahead and make the realization that x is 0 when y is 7. That's what it's saying. Or they could have given us the point 0, 7. We're going to plug that into our general solution to solve for c. So I have 7 equals c e raised to the negative 3 times 0 squared. So that's going to be 0. So you end up getting 7 equals c. So when I write out my solution here, I have y equals 7 e to the negative 3x squared. That is a particular family member. There's infinitely many solutions here, and there's only one here. Now this one still is explicit because it's solved for y, but now we call this a particular solution. because there's no c's. Now we can get into a lot of theory here about existence and uniqueness, and there is a theorem about that where there exists one solution that hits the point 0, 7, but we're assuming that y prime needs to be continuous on a rectangle. So things can get more complicated. But I'm going to go ahead and show you a few things, and I don't know if it's going to be blurry, but I'll include this in the PDF that's on my website. This differential equation here, this guy right here says y prime equals negative 6xy. That actually represents, you may remember this from Calculus 2, a slope field. Now, how is that coming out? Well, if it's blurry, once again, you can check out the PDF online. Now, when we solved this system, we got infinitely many curves. So, you could put a 7 in there like we have here, or a -2. And so I went ahead and plugged in lots of values of c's, and I graphed the solution of that differential equation onto the same thing with the slope field. And notice what is happening. Those curves are following the slope field. And there's infinitely many curves. I don't have infinitely many drawn, because if I had all of them drawn, you'd see a lot of, it looked like it was painted red on lots of parts. Now, this one right here, where they gave me the initial value of 0, 7, they're basically giving me a point. Now, this is going to be probably a little harder to see, but there's the point 0, 7. And I want to know which one of those family members, there's infinitely many, go through that point. So the existence and uniqueness theorem says that we can find a particular solution, and the particular solution is that one right there. That is the one that was y equals 7e to the negative 3x squared. Now, in your homework, you won't have to show graphs, do anything crazy like that, but I show that to you because I know some of you guys are picture people and you appreciate the pictures maybe. Let's go ahead and do problem number 4. So we've just finished 3, which was an initial value problem, and problem 4 is this differential equation right here, dy dx equals that fraction. So first of all, we have to ask ourselves, is this separable? Can we separate the right-hand side through multiplication? And the answer is yes. The first function, which I think we call g of x, would be 4 minus 2x. And the second function, h of y, would be 1 over 3y squared minus 5. So this can be separated through multiplication, which means I'm going to go ahead and do a cross multiply. Or multiply by the LCD in any case. I'm going to end up getting 3y squared minus 5 times dy equals 4 minus 2x times dx. So that's what I have. And I've actually, just by doing that cross multiply, I have separated this equation. Y is on the left, x is on the right. I'm going to go ahead and integrate both sides. Whoa. And when you do the integral of both sides, you end up getting y cubed minus 5y. I'm going to put the c on the right hand side. This equals integral of 4 with respect to x, 4x minus x squared. And then, of course, we have plus c. Now here's the deal with this one. We really do not have the skills at this moment to solve for y. I know some of you are like, we can factor a y out and divide by y squared minus 5, but then you'll have y equals an expression that has a y in it. So there's no way we can solve for y here. In your homework, you're going to want to solve for y whenever you can, but on this one, you simply can't. So this right here happens to be your solution. That's the solution to that differential equation. Now this is still a general solution, because it has a c, but it's not explicit anymore. It's not solved for a y. It's actually, you might remember this word from calculus, implicit. So this is an implicit solution. And implicit solutions do have a disadvantage. And, first of all, you can't write it as a function. We'll show you the picture of some of the family members after we do the IVP. Okay, so the IVP, the initial value problem, set on this problem here means we are going to plug the point 1, 3 into that general solution to solve for c, and then that will give us a particular solution. Both will still be implicit. So when I do that, I end up getting y cubed, so that's 3 times 3 times 3, 27, minus 5 times y, so that's going to be 15. This equals 4x is 1, minus x squared, plus c. So what we have here is 12 equals 3 plus c. c equals 9. So that's not our answer, c equals 9. What our answer is going to be is writing out this with a 9 there. So y cubed minus 5y equals 4x minus x squared plus 9. And this right here is my solution. It's not a general solution, it's a particular solution. Abbreviating there. And it's still implicit. Okay, because it's not solved for y. And so that completes problem 4 and 5. It's cloudy, so it's getting darker in here. Open up the blinds there. Let's go ahead and show you a picture. The slope field for this guy and some of the solutions that we have here. So some of these guys look like that. So that's kind of weird. So you actually have the point 1, 3, which was the point right here. And when we wrote out that particular solution and it said y cubed minus 5y plus 4x minus x squared plus 9, that is actually the curve that looks like this red curve. This red curve is not a function. It has, well, it doesn't pass the vertical line test, but it also has some vertical slopes. So sometimes we would say that that solution that we wrote, and we're not going to get picky in the homework or on the test, but that solution cannot be valid from negative infinity to infinity. There's the sun. Okay, so that. We had a passing cloud there, and then there's, oh, this is great. I'm going to go put my Good and Annan book right here. Hopefully it doesn't make things too dark, and hopefully I don't knock down the tripod. We're just going to have to live with those pieces of sun right there. And then what will happen is it will get dark again. So it's beautiful. But at least we're getting this on YouTube, I hope. So this right here, we can't, this is getting darker. Okay, so this solution right here is not valid from negative infinity to infinity. It's valid, you don't have to write this down, from like -1 to 5. And we can go a little further than that. We can make the interval bigger, but once you go past an x value that goes past this vertical tangent, then you're in trouble. So sometimes if you have to take another differential equations class, they'll tell you, hey, write the interval where the solution is valid. Now, if we had picked the point 1, 0, instead of the red family member, the green family member would be the one, that would be if c equals -3, and it would actually have 2 branches. And so if you pick the point 1, 0, this solution is right here. It would only be valid from like 0 to 4. You wouldn't want to go from negative infinity to infinity because you're stuck on this little thing. And then if we had said, oh, here's the initial value problem, and it was 1 comma negative root 5, which is right there. Now this one is the branch of the green one, and this solution would be valid from negative infinity to infinity. So this is the disadvantage of implicit solutions, is if you're given an initial value, you might not know the interval that it's valid on. Let's go ahead and do our next problem. So that was problem 4 and 5. Let's do number 6. So these are the kinds of things you get in your homework. Separable equations. Check right there. Yes, we've got nice. I should get something taller. Maybe I should put my hand right there. Oh, hold on. Okay, so if I hang this right here on the midi blinds. Oh, come on. No, what's happening here? There. Ah, you gotta be kidding. Okay, so here it goes. Okay, so I'm doing a better job now. I hope it's not my arm that's blocking it. Oh, man. Oh, come on. And the midi blinds keep shaking too, so that changes everything. Okay, well that's just going to stay. You think that I could actually be talented enough to get rid of those dots there. Oh well. It actually, this is the highlight of the video. And we are at the 26-minute mark. Okay, let's go ahead and solve this differential equation. This differential equation is separable. The function of x that's on the right-hand side is, I guess we can call it g of x equals 1 and h of y equals this. So we can separate this. I'm going to multiply both sides by dx. So I have dy equals y squared minus 4 times dx. I'm going to go ahead, I don't have the y's all on one side. I'm going to divide by y squared minus 4. So I have dy over y squared minus 4 equals dx. Okay, now we've divided by something, so some values of y that are not allowed here would be y equals 2 and y equals negative 2. So are they even solutions? Let's go ahead and take their derivatives. Y prime equals derivative of a constant is 0, and then y prime here, the derivative of this constant is 0. So let's put y equals 2, y prime equals 0 into this equation. Remember, dy dx is y prime, so I have 0 equals 2 squared minus 4. So this guy right here is a solution. Now, the one right here, let's see if, oh yeah, no, we don't, definitely don't. Oh, look at that. I got rid of one of those spots there. Hopefully it's not too dark now. Here, I've got a light. Let's put the light on. Oh man, just blinded myself, and there's that spot. Well, anyway, it is what it is. What are you going to do here? You put negative 2 into this equation, you end up getting, well, y prime is 0. 0 equals negative 2 quantity squared, so that is 4 minus 4. So this right here is also a solution. See if the light made things worse. Okay, well, I didn't experience this problem before with the sun coming in here. Anyway, so let's make sure at the end we make sure that y equals 2 and y equals negative 2 is included, and make sure we did not leave one of them behind at the gas station. So I'm going to go ahead and integrate both sides. When I integrate both sides, see, we're missing a lot of things by not coming to class. So if we were in class, I would say, hey, guess what, guys? I will do the right-hand side, and you do the left-hand side, and I'll even collect your C. You know, but now, if there's any humor in that, if there was, some of you didn't find any humor in that, it's lost because I'm sitting here doing videos. This guy right here, you want to take the integral of them. Some of you might go, oh, it's an inverse trig function or whatever. This right here happens to be the technique of partial fraction decomposition. So you've got to write this as y minus 2, y plus 2 on the bottom. And you have to decompose it. Kind of sounds gross. A over y minus 2 plus b over y plus 2. Partial fraction decomposition is going to come in big time when we do Laplace transforms. I'm going to go ahead and multiply this by the LCD. I didn't leave much room over there, so I'll put it over here. Y minus 2, y plus 2. And so what I end up getting is 1 equals a y plus 2 plus b y minus 2. I'm going to go ahead and plug some y values in. Now some of you might say, oh, my teacher in the last class told me to multiply that out. Well, you know what? It's a free country. Well, it's not as free as it used to be because of the shelter in place, but go ahead and do that if you want to do that. I'm going to cover up the problem here. And I'm going to get 1 equals a times 0. And then we have plus b. Negative 2 minus 2, this is negative 4. Looks like b gives me negative 1/4. Now I'm going to let y equal positive 2. And that's going to give me what? I plug it into this equation here. 1 equals a times 4, because 2 plus 2 is 4, plus b times 2 minus 2, so that's just 0. This is going to give me a equals 1/4. So now I can rewrite that guy right there as, sure hope it didn't go through. Oh, it did go through. Ha ha ha. Sharpie, you're my enemy. And, well, it actually smells pretty, this smells good. Sharpie, you're not my enemy. I'm getting dizzy. Oh, my. Too much Sharpie pen. Oh boy. I gotta close some of those other Sharpie pens that I have laying on the desk. Just had a little dizzy spell there. Oh, what was I doing? So look at this. I have 1/4 over y minus 2. And then this is going to be plus a negative 1/4 over y plus 2. So that is what we have there. I hope that headbanging thing did not blur anything. I don't think so. I see a line of light. Okay, well, I think we're doing good. I'm going to go ahead and see if we have any. Oh, look at this. I can now open this a little more. There we go. Perfect. I can turn that thing off. Whatever, I still have a little bit of light there. Okay, so let's go ahead, and what we're doing is we're rewriting, doing some paper folding here. We're rewriting the left-hand side of the equation. So when I do that, I end up getting 1/4 over y minus 2. And then this is minus 1/4 over y plus 2. And wow, I'm kind of made it go down a little. That is what 1 over y squared minus 4 looks like. I'm going to integrate. That's what I'm integrating actually. This is dy. Okay. So we can get rid of this piece of paper, or we'll include this in the PDF, okay? Some of you might want to relive that. Let's get rid of this orange dot here, because this could throw loop into our calculations that we don't want. So the integral of 1 over y minus 2 you can do a u substitution. In any case, you're going to get 1/4 ln absolute value y minus 2, and then this one's going to be minus 1/4 absolute value, ln of the absolute value y plus 2. And then we'll throw our c on the right hand side. This is going to give me x plus c. Okay, now I'm going to try to solve for y if I could. And so the next thing I want to do is I want to multiply this equation by 4. Okay, so I have ln y minus 2 minus ln y plus 2 equals 4x plus 4c. And 4c is really what? A constant c. You don't have to make the constant in green, but I just wanted to use the green pen. I had an urge to use the green pen, and there it went. Now, I'm trying to solve for y. I have properties of logarithms that say if I have ln of this minus ln of that, I can write that as a quotient. It's called the quotient rule for logarithms. And we have ln, absolute value, y minus 2 over y plus 2. This equals the 4x plus c. So we're going to be taking the problem up here, right next to our 2 children that hopefully we did not leave any of them at the gas station. The next part that I'm going to do is I'm going to exponentiate both sides. And so what happens here is we have that property of logs where that thing goes pop. And on the left hand side we have absolute value y minus 2 over y plus 2. This equals e to the 4x plus c. Okay, so we have y minus 2, y plus 2. This is e. Oh, I wasn't putting my c in green. That's all right. This is e to the 4x, e to the c, and e to the c is what? It is a constant. So I'm going to write my constant. You know what I'm going to call it? I'm going to call it c. That's right. It's a different c than that c. Now, the c can absorb the absolute value, which we've seen in other problems. And so I have y minus 2 over y plus 2 equals ce to the 4x. I'm trying to solve for y, so I want to multiply both sides by y plus 2. When I do that, I end up getting y minus 2 equals y plus 2 ce to the 4x. Okay, so y minus 2 equals ce to the 4x times y plus 2ce to the 4x. Now some of you might say, well, 2c can be replaced with a c, but now you can't do that because you have another c here. So if you're going to replace 2c with a c, you better replace this one with a c over 2, because these c's have to be the same c. Okay, you don't want to turn it into c1 and c2. You're only going to have one constant on these first order equations. So what am I trying to do? I'm trying to solve. Look at this. My x lost a leg. Hopefully I didn't say e to the 4. Okay, so, oh no, now those guys are touching. That's forbidden. Oh well, can't do anything about that. Okay, so my y terms, that guy right there, and this guy right here. I want to get my y terms on one side and my non-y terms on the other side. So in order to do that, I'll go ahead and I will subtract ce to the 4x y, and then I'll add a 2 to both sides. So this equals 2 plus 2ce to the 4x. Another piece of paper. Well, this problem's going a long time. The partial fraction decomposition, I mean, that was just part of the fun. Okay, I'm trying to solve for y here. I have all my y terms on the same side of the equation. I'm kind of almost done here. So I'm going to factor out a y. 1 minus ce to the 4x. This equals 2 plus 2ce to the 4x. I'm going to divide both sides by this right here. And so now I have a y equals. I'm going to factor the 2 out. This is a matter of style. I could just write that as my answer. I'm going to write my answer as 2, and then I have 1 plus c e to the 4x, and on the bottom I have 1 minus c e to the 4x. And so you could just have written this right here. The factoring out the 2 didn't help reduce it or anything, and so we have our answer. Now, the question is, did we leave any of the kids? Here are the kids right here. Here are the kids. Did we leave any of them at the gas station? And, well, can you put a value of c in there where you'll get one of the kids? Well, c equals 0. If you have c equals 0, you end up getting y equals 2, and then that's just going to be a 1 there. 1 over 1. So we got that guy. If you make c any other real number, you're going to have e to the 4x within your solution. So what happened is we actually left this guy at the gas station. He is not included in this general solution here. So we have to write y equals -2 right next to the solution, because we cannot think of a real number c that will give us y equals -2. Sometimes this guy right here is called a singular solution. So that completes this problem, problem number 6. Let's go ahead and look at problem number 7. So problem number 6 was, it looked like this differential equation gives this slope field here. Now I'll give you a few of these family members. There's infinitely many. Here are a few of the family members, and they follow the slopes. Let's go ahead and get rid of the slope field. And so one of the family members is that red curve. It has 2 branches. Another family member is that blue curve, and another family member is the green curve. But there's infinitely many curves we could have drawn there. Those are for the people who like the pictures. So let's go ahead and do problem number 7. Problem number 7 is pretty much the problem that we just did, except I'm going in IVP. So can we do an initial value on this one? Yeah, I mean, this is really 1, 0, which we are going to place in there. See what we get. We end up getting 0 equals 2. Would have been better if it said y of 0 equals 1. Oh well. 2 times 1 plus x is 1, so this is going to be c e to the 4th. This is all over 1 minus c e to the 4th. So what I did is I put 1, 0 in for x and y there. Okay, I'm going to multiply both sides by that denominator, 1 minus c e to the 4th, and it's just going to be multiplied by 0, so really I'm going to end up with this. I'm going to divide both sides by 2. The 2 goes away. And I'm going to solve for c. When I solve for c, I end up getting negative e to the -4. okay, because I will subtract 1, that gives me the negative, and then I'll divide by e to the 4th, and actually I pull him upstairs so he looks like that, and that's just a style thing. So let's go ahead and write out my solution for this one. This particular solution is going to be 2, we have 1 plus, oh, there's a minus there, so it's going to be minus e to the negative 4, e to the 4x. This is all over 1 minus, and then I have negative e to the negative 4, e to the 4x. So, like, if you're wondering what I'm doing, I don't even know what I'm doing anymore. It's really complicated. I'm actually putting c right there. And so let's go ahead and clean up this answer a little. This is y equals 2 multiplied by, on the top you have 1 minus e to the 4x minus 4. And on the bottom we have 1 plus e to the 4x minus 4. And that is not a general solution, it's a particular solution, and it's also explicit because it says y equals. Now in terms of the picture, what does that look like? We have the point 1, 0. This guy is the blue one. And there's the point 1, 0. That's what this is. This right here, if you graphed it on a computer algebra system, it is the blue family member and it goes through that point. So that's what we just found. Let's go do one more of these. Same problem. The initial value given is y of 0 equals negative 2. So we have the point 0, negative 2. I'm going to go ahead and plug that in to the differential equation. So when I do that, I end up getting negative 2, that's for y, equals 2, and then we have 1 plus c, 1 minus c. So I'm plugging this x and y value in for here, and I have negative 2, 1 minus c equals 2, 1 plus c, negative 2 plus 2c equals 2 plus 2c. Subtract 2c on both sides, I get negative 2 equals 2. Oh man. Okay, so that's, we could even make the tears be blue. So that's bad. What happened? I thought there was this uniqueness, existence and uniqueness theorem. What happened is this. This is the point where x is 0 and y is negative 2. Well, that's certainly not going to happen up on this one because of this. But look at this. Look at our singular solution. That's where this point 0, negative 2 lies on. It lies on this horizontal line, y equals negative 2. So this right here was a waste of time. But it isn't every math class you take. We waste lots of time doing just writing symbols on the board. So it might help when you are given an initial value just to check really quickly if it lies on the singular solution. And you can save yourself this right here, especially this. We don't want to do this. So that is what it is. Let me go ahead and show the picture on that one. And some of you may have been wise to this right away. The point that we were given was the point 0, negative 2. 0, negative 2 is right here, and there's your singular solution, y equals negative 2. So that completes number 8. Let's go ahead and do, just get you ready for something in your homework. So in your homework, there may be a problem or two where it asks you this right here, and I'm not going to work out this whole problem. I think this was like number 18 in the book. Find an equation of the curve through 0, 1/2 whose slope at xy is negative x over 4y. So that looks pretty weird. Except the fact is they say the slope. And the slope, well, the letter for slope is m, but then we also know that y prime represents the slope. The slope at that point is negative x over 4y. So when they ask you in your homework to do something that looks like this, they're really asking you to solve this differential equation with this initial value. Y of 0 is 1/2. So I'm not going to do that just because I wanted to get you ready for questions like that in your homework. The applications of differential equations. It's the backbone of physics and electrical engineering, other engineering as well. It's a tool for biology and economics. We can look at orthogonal trajectories, pendulums, springs, circuits, population models, banking. The list just goes on. We will see applications. We will do mixing problems in Chapter 1. We'll do circuits and springs in a later chapter. So this concludes section 1.4. We'll see you for the next section.